Sorry about that, sorry. Check this out.
Good afternoon on the Space Coast of Florida.
Will the cable,
It doesn't move.
it doesn't reach all the way up there? Ah, okay, so my presentation for the teachers is not on the thumb drive.
Yeah.
So you just have to connect my laptop, and you have
Your
to use my
laptop from
laptop.
here is okay.
Is fine. So either I can use my laptop this way and advance my own slides. Maybe I'll do that, and I'll talk from the floor.
Pen drive แล้วป่ะฮะpointer ป่ะฮะ Okay. Allez, den beginningsplats Fadil ska
No. Hold on. Okay, now. There's okay. Okay, but there's no sound.
No, there will be. There's no sound. You will not be needing.
No. Well, you can leave it, don't unplug it now because you make a lot
Yeah,
of
yeah,
noise.
that's okay. No, I thought you'll be using sound. Yes, you can use that here.
Oh, nice.
It's already connected.
Nice. Okay.
Yeah, it's like.
Very good.
So
Thank you. Yeah.
and now, and you see the lines.
Yeah. All right. Thank you.
Okay, good. Welcome back, everyone. So we'll start with the second part of the day, and it's going to be very informal. There's one presentation by Mr. Jim Adams. I would say not really presentation, but mostly interaction. And feel free then to ask your question. This is your time. Ask all your questions. We have dedicated this session specifically for you. Good? Ali. Floor is yours.
Thank you. How many of you were in the earlier session? Okay, so everyone, we don't need to like do the bio or anything like that all over again. When I heard that I was going to be working and with a group of teachers, I realized that this is actually the first time I've ever had just the teachers alone without the students. So I started thinking, what would I tell teachers about space exploration that they would want to know? And I hope I got it right. It's a very different kind of presentation than from this morning. This is more factual and resource oriented. And I'm more than happy to answer questions along the way. So that's me. And this is Mauritius. Right there. At least that's what I'm told. So. There we go. Okay. So the question is, why should we use NASA resources in a classroom? I was just talking to somebody about this earlier. NASA and space exploration, and that's the other thing. I will make this presentation available. Audrey, if you collect interests like email addresses, or if you have some other way of distributing it, we'll distribute this to anybody who wants it. Okay, so Audrey's the lady, right? Anyway, the bottom line is that NASA, as part of its mission, communicates what it does to the public, and that includes classrooms. That includes making everything available to teachers, and not just to the United States, but to the world. So that means if you find an educational resource on NASA's website, it's copyright free, and it means that you can use it without having to go get a license or pay a fee. On most of my slides, I have a link, which is why you probably want the slide deck so you can extract the link. But NASA has thousands of resources that you can use that cover grades kindergarten all the way through 12th grade. NASA's Office of STEM Engagement is created specifically with the challenge of keeping NASA's content fresh and relevant to teachers. And so they do that in a variety of ways, but one of the big things that they do is they create a community of educators that helps them understand what the teachers need. Sometimes it's inspiration, sometimes it's technical information, sometimes it's lesson plans. You can find almost all of that on the NASA education website. For those that haven't figured it out yet, this spells Mauritius. So you can, there's a website where you can go and have NASA in Earth Science data spell your name or the name of your school or whatever else you put in there. So I did that last night. There's a central hub, kind of alluded to that earlier, about that tries to gather up all of these different educational resources. The reason it's I make it sound like a big job is because there are 10 different NASA facilities across the United States, and every one of them has their own education group. So there's a lot of stuff. Not very much of it overlaps, so it's pretty deep content, everything from rocket science to physics to earth science, to art even. And you can filter, we'll take a look at that in a little bit. And oftentimes, as I said, there's guides, there's interactive activities, podcasts, videos, lesson plans, a variety of different. Okay, you saw this video earlier. How many of you want to see the rocket launch again? Just one more time? All right. Oh, no, too bad. Yeah, I didn't program it, so have to remember to understand. And maybe later we'll play it again. So one of the things I find really interesting is that people are just curious about how the people build these things. And there are places that you can go on the NASA website to watch what's going on inside the clean room live. And it's actually a little bit addictive. But if you go to the Jet Propulsion Lab, that's one of the premier places where we build. This happens to be one of the Mars landers that they're putting together. I believe this one is called Insight. And so a lot of the JPL research is on Mars focus. You can get to a podcast and video called Mars in a Minute, and there's the link for that. I think one of the things that I learned about Mauritius is y'all are concerned about oceans. And that's a thing that NASA is interested in too. NASA has an extensive partnership with an organization in the US called NOAA, the National Oceanic and Atmospheric Administration. And together they generate resources for educators and for children to begin to understand our oceans. There's tools that not only researchers can use, but also adults and children can use to begin to understand the data that NASA takes and how that affects their lives. This happens to be sea surface height. So the ocean isn't flat; it has highs and lows. And no, I'm sorry, I take it back. This is gravity. So we sent a pair of spacecraft to circle the Earth, and by measuring the distance between them and how that changes, we were able to determine the change in the gravity, say, between this spot and that spot. And then we run a thought exercise sometimes with the students and say, what is it that could change the gravity of the Earth underneath in a local condition like that? Of course, the answer is minerals. Some of it could be water. There could be gaps beneath the surface. And so one of the ways that we teach about gravity is by looking at the way it changes on the moon. We also have art experiments. So art, not modern art, but we have ways that you can coach students in drawing, for example, the art of a spacecraft. There's another one on how to draw a rocket, right? And along the way, then the students are learning about the various pieces of a rocket, and it's an opportunity to teach them how to. You can log into NASA Live and watch the astronauts living their lives on board the International Space Station. At first, I thought that was a little creepy, but it turns out astronauts love being watched, and people like understanding what it is that the astronauts are doing on a daily basis. So, what is it like to live in microgravity and understanding Newton's laws? The ARISS is a program with amateur radio, ham radio. So there's a couple of repeaters on board the International Space Station where students can actually send a signal to ISS and get it bounced back, and they can log that in their radio logs. So there's again another one NASA Live. By the way, this isn't a very long presentation, so what I'm really mostly interested in is Q&A. So it's going to be next. Citizen science is a misnomer. You don't have to be a U.S. citizen participating in citizen science. Citizen science is just non-professionals helping out to do science. And there's hundreds of projects that your students can do to help out real scientists trying to analyze data. Everything from counting craters on the moon to understanding the interaction between the sun and the earth and its magnetic field to watching, I believe it's algae blooms in the ocean. All sorts of things can be done. So you go to nasa.gov citizen science and you can learn about ways you can get your students involved in that. This may be more for the US folks, but in a sense they're not trying. There are webinars and workshops and newsletters that are free to everybody. There is an artifact program where classrooms can borrow like a moon rock or a piece of space shuttle tile or something like that. Sadly, I think that is open to just US. But it's no harm in asking the US Embassy if they could arrange it. We can always say no, but we could certainly give it a try. Space grants for sure are US only. But there's a fund that gets divvied up amongst all 50 states to do space education through a grant program. Let's see. Yeah. So, if you're teaching biology, you could talk about extremophiles. What's an extremophile? You go down into the oceans and find thermal vents, you find life living in places that you would never expect it. How is that important? It's important because it's an analog of what we may find under the ice shelves of Europa, which is a moon of Jupiter. And under Europa's ice shelf, scientists think that maybe we might find life. Probably not fish, certainly not mermaids, but definitely maybe algae or microbes, absolutely. Just the other day, I sat with a physics student who was a chemistry student, who's having trouble getting fundamental stoichiometry. It's like chemistry 101. It's like putting two elements together to make a new molecule, and how much of one do you need to make the whole thing, and that's what stoichiometry is. The moment I showed him how the hydrogen and the oxygen go together on board that rocket that we saw this morning, he started to get it. He started to understand. So real world examples from something that inspires students help. And I don't need to tell you that, but I can tell you that NASA has lots of them. One of the things that keeps coming up on the NASA website is don't bite off more than you can chew at first. Start with something small, and then you can scale it to something bigger. Let's see. Why did I put this in? Oh, this is just how you can search for lesson plans. So it has an extensive search tool. You can go to nasa.gov, search lesson plan, and find a whole variety of different examples and lessons that NASA can help you with. I think the laser pointer is tired. There we go. All right, multimedia. NASA is known for its multimedia. There's several sites at NASA, but my favorite is images.nasa.gov, and you can find almost anything that you're looking for. This happens to be a nebula that I also think is really interesting. Looks like an eye in the back, but that's a star collapsing into a black hole, and this is what's happening to the dust cloud around it. Oops. Okay, so if you get really aggressive, you can start a robotics program, maybe an after-school robotics program. How many of you have heard of FIRST Robotics? Nobody. Maybe I was one of that. Yeah. So there's a group called FIRST Robotics, but there's others. that hold robotics competitions. And NASA is a big supporter of robotics. In this particular case, these teams meet and they compete. They each have a challenge that's announced in January, and they have until March to build a robot that meets that challenge. Sometimes it's throwing a basketball and making basketball hoops. Other times it might be playing ping pong. A variety of different things that the robots have to do in a competition, and it takes on a very exciting profile. The kids learn a lot, not only about physics and electronics and mechanical engineering, but they also learn about social interaction, leadership, and collaboration. I will say that the biggest problem that NASA has is keeping track of the impact. Because there are laws in the United States that prohibit us from tracking students after they're in school. So maybe you could do that here and we can talk about, so maybe you have the same notes. Okay, so I'm done. This happens to be my pet project, right? And about the only time this week that I have plugged my own thing, but we have a program called Book of Scientists. You can find it at bookofscientists.com, and we bring in twice a month renowned scientists from around the world to talk about a variety of topics. It's all geared for 10th graders, when we get 9-year-olds to 7-year-olds. Right? It's all free, right? And the part of Book of Scientists is the question and answer. So the scientists are limited to talking for 30 minutes, but then the Q&A goes for 45. And once it's over, the students are they're allowed to take a quiz, and they earn a certificate for participating. Pretty simple, but it's engaging for a lot of people. And maybe your students will want to participate now. It's usually on Saturday mornings in the US, so that would be Saturday evenings here in the wishes. And that, again, is all I got. Yeah, that's it. So with that, I think we'll just do Q&A. And hopefully that was helpful. Audrey will make sure that you get the presentation somehow, right? And embedded in the presentation are lots of links that you can follow and probably spend a lot of time surfing the web. No, everybody's asleep. It's been a long day, huh?
Yes, I was saying I had to cut short in the morning session because the VIPs had to move, and we now have all the time, like we have a lot of time. Not a lot, but you have more time to ask your questions and interact. Yes.
Hello everyone, so question is, how do you make sure that we avoid the same fate, the timing one or earlier? So what are the things that we can learn from that, and we can make sure that it doesn't happen again? Because
you're talking about when we have an accident or near miss or something like that? Well, sadly, there's only been fortunately, there's only been a few accidents, all of them sad. In NASA's history. One of the first ones we didn't talk about this morning was Apollo 1, where the 3 astronauts were in a dress rehearsal for a rocket launch, and they flipped the switch, and their capsule caught fire. And they couldn't get out, and they died. So it was a big investigation trying to understand what happened. It wasn't about affixing blame, but it was trying to make sure that it never happened again. And that's been in NASA's culture since the beginning, and that particular accident was one of the very first. Later, there was the Challenger accident, which was 50 years ago this year. And I remember when that happened, the entire space shuttle program was shut down for about 2 years while we figured out what went wrong. And we talk about, at NASA, we talk about proximate cause and root cause. The proximate cause is the solid rocket motors burnt through the O-rings and caused the hydrogen tank to explode. But the root cause was that the team had, especially the management team, had tunnel vision, and they were ignoring the signs that said it was not time to go. Temperature was too cold. There were some people saying that the O-rings wouldn't hold, and the management said, no, this has happened before, we're not going to, there's no danger, we're just going to move forward, and they were wrong. So those sorts of things get built into the NASA culture, to the point that even today, if you are sitting in a meeting and something's not going right, and you say, I have a dissenting opinion, that's a code phrase for stop and listen to me because something's not right. You can still get overruled, but at least you'll have your voice. And that's key to the NASA safety culture. I will tell you that as NASA gets more and more successful, the risk of having a failure becomes more and more dire. If we had an Artemis mission blow up on the launch pad, that would be it for the moon program for probably a decade. And so we take safety and security very seriously, and we always know the risks that we're accepting when we go to launch, when we go to land, when we do a variety of different things that are so we understand it. And even the astronauts know that they're taking risks with their own lives, and they know exactly what those risks are. So I hope that answered the question. Pontificate just a little bit. Anybody else? No, you're all tired? Oh, she's got me.
Good morning, everyone. I just wanted to ask a question concerning our curriculum in physics. And is there any policy decision where you have to discuss with the ministry about the curriculum to integrate the
So you're asking, is there a way of interacting with NASA about the lessons that you find? Sometimes there are credits to the people that put it together and contact information, and other times there are. But there's always an info@nasa.gov email address that you can write to, and hopefully get an answer to your question. I can't guarantee it, but I can say that we do try to respond back. So, if there's enough questions, sometimes that's going to hold a workshop. Maybe they don't have the lesson plan correct, or maybe it's not useful. That's not all I know about that. But we definitely want to keep it correct and fresh. So, that's our report.
It's not work, she works one like a thing.
Hello again.
Hi.
Quick question about NASA resources for students who are interested in internships or some sort of practical hands-on experience. What opportunities does NASA, NOAA, various organizations in the United States have for foreign students to experience?
So they're limited, of course. Right? And generally, the
foreign students that have those opportunities are the ones that are already in university. So if we're talking about high school level and below, the opportunities are quite limited. But you can think creatively, like maybe create a program with the University of Mauritius, and then have the University of Mauritius partner with, I don't know, the University of Wisconsin or something. And together they could work on an asset project that often will result in briefings and interactions with NASA scientists and engineers.
Questions?
Thank you. So what we knew is that there were 6 women-led expeditions, which were between 69 to 72. But why, since then, we don't have women-led expeditions to selection?
That's a really good question. So the answer, it lies in budgets and geopolitics. So at the time that we went to the moon in 1969, we were in a race to demonstrate US dominance of space compared to the Soviet Union. We don't have that kind of issue anymore. Thank goodness. In 1972, it became obvious that the moon landings were outrageously expensive, and the United States was dealing with other problems at home. So we stopped it and said, our long-term vision now is not to go back to the moon, but to build a space station so that we could begin to understand how to live and work in a long-term way in space. Instead of going to the moon for 3 days and coming back, now we send astronauts for 6 months or a year to live and work in space. And like I said earlier this morning, they're guinea pigs. And we begin to understand the impact that space has on their bodies and their minds and their abilities. And so, so we did that now. For 25 years, we've had astronauts in space living and working and being guinea pigs. So it's time now to end the International Space Station thing. Why? So that we can move on to the next thing, which is putting an outpost on the moon and hopefully creating an economic environment that encourages commercial business growth as well as other opportunities. So budgets and geopolitics.
My name is Nadine. I also have a question about the first session. You mentioned about the Artemis 2 mission that all the systems were activated except the waste management system. I'm curious about how the astronauts managed, how the troubleshooting went, how they managed for 10 days.
Do you really want to know? Can you
I
share?
do, yes.
How many of you have junior high schoolers in your home, like grade 6, 7, and 8? Or in your classes, are you grade 6, 7, and 8? 7. 7 and 9. Okay, well, anyway, the bottom line is they use diapers. and it's not pretty, and you can't be modest if you're living in a volume the size of an SUV for 10 days with other people. But you know, it's a function that everybody has to conduct. So so they took care of it with what we call Plan B, which is diapers. So, by the way, the Apollo astronauts did the same thing. They didn't have to wear it at all. So.
It's one more question.
So, I want to talk about this microgravity and how it actually rises.
Sure, yeah. So microgravity is the correct term of zero gravity. Because you're always under the influence of something. Either the Earth or the Sun, right, or the Moon, or Mars or Jupiter, that sort of thing. And it's just not the same pole as we have the acceleration, I guess is the right word. Same acceleration as we have here on Earth. Right? Because the further away you get from an object, the lower the gravity it tapers off. So in space, we refer to it as microgravity, even though lots of people like to refer to it as zero gravity. Microgravity keeps things in orbit. That's how the International Space Station orbits the Earth and doesn't fall down. It's moving fast enough that microgravity just bends the velocity vector enough that it keeps going around the Earth. When you get to the Moon, you not only have the effects of microgravity from the Earth, but you also have the effect of gravity from the Moon, which is what, 1/6, I think, of the Earth's gravity. So the fact is that gravity is always there, and we just have to account for it. Yeah, I think I answered your question. So, if you let something go in the International Space Station without giving it any momentum, it's going to stay where you put it in the International Space Station, but it's still moving, right? It's just moving at the same rate as the International Space Station is. So it looks like it's not moving at all. And that's the way microgravity works in the International Space Station. I remember when I was helping to design the International Space Station, we were trying to create a facility section of the International Space Station that was as free from extraneous accelerations as possible. We could never get rid of the microgravity. Right? So there was always a little bit of gravity. But one of the things that was a huge disruption to that quiet gravitational environment was if an astronaut were hanging onto a handrail somewhere else in the International Space Station and sneezed, you would feel it all the way over in this microgravity facility. You would see it in the movement of the space station around this object that was floating. So it's a thing we constantly have to account for. We use it to our benefit, and sometimes it gets away. Okay, are we done?
One more
Oh, there you are.
question.
I thought I saw you leave.
One last question from my side. On the 15th of April this year, we had an interaction with Mr. Alexandra, who is a Russian cosmonaut and aerospace engineer. During his speech, we had an interaction with him, and he did mention about something like space pollution in his speech. I would like to know from you if it is the case that space exploration is causing space pollution. If yes, what NASA is going to counteract that?
Yeah, good question. The answer is yes. That for many years, we would launch a rocket into space. Usually the second stage would stay in orbit, but it was dead, it was inert, and it just sort of drifted. But there were only a handful of them, and so we didn't actually worry about them too much. We could track them because we wouldn't want to run into them. But now, with the dawn of CubeSats, you know what a CubeSat is? It's a 10-centimeter cube. That's an entire satellite. And they're so affordable that high schools are building them. And they're so inexpensive to launch that we've got thousands of them in order. And anytime one of them runs into another, doesn't matter if it's a CubeSat or two larger objects, it creates a cloud of debris that stays in orbit. Now, what generally happens is in low Earth orbit, we try and design them so that once we're done with them, we start to skim along the upper atmosphere, and slowly but surely the atmosphere slows down the spacecraft, and it re-enters and loses velocity, re-enters and burns up on the way. Sometimes that doesn't happen. And now, with the dawn of the mega constellations like Starlink, there's more and more stuff that we have to avoid as we launch to go into deep space. And that does concern me. Orbital debris is a big problem. And what NASA does with every one of its missions is assure that we have a disposal plan before we will launch. So how will we deal with that now? But that doesn't mean that we don't still have a problem, because it's been decades of really not paying attention to that. In fact, it's such a big problem that the UN Committee on the Peaceful Uses of Outer Space, which meets twice a year at Vienna, always discusses progress on mitigating orbital debris. The thing is, you can't just go catch it, right? You can't just go grab it in space. There was, I was telling somebody earlier, there was a space shuttle mission that returned from space, and when they inspected it, there was a divot. It didn't go all the way through because the glass was very thick, but yeah, the divot in one of the windows. And why was that? At the center of that divot, they found a paint fleck, which interestingly enough, they were able to trace to a Russian rocket. But yeah, a paint fleck moving in the opposite direction as the space shuttle caused this enormous gash in the window. So it's a big physics, conservation, and momentum problem to figure out how to capture this stuff. And there are people out there that want to try, and I guess I would say, if you don't try, it won't happen. But there is it's a big problem to try and capture it. One of the ways that NASA was looking at dealing with orbital debris, this was back in 2014, so a number of years ago now, was that if we could remove one of the big things every 3 months, if we had a mission that would go and grab, say, the second stages from previous rockets, then we would be able to keep the cloud that forms down to a manageable minimum. But since then, the rise of things like Starlink have created 1,000 times more objects in space to have to worry about. It's a big place, space, and so there's still, for now, the opportunity to be able to launch. But that's what I really worry about, is being able to get off of Earth. There's also astronomers that worry about it because it affects their view. If you're trying to operate a telescope and then suddenly orbital debris is going overhead, it's blocking the stars. So it's a big problem. But maybe you'll teach a student that will go on to fix that. We'll see. Anybody else? I hope everybody's tired.
Do we have 4 questions? Take one last, maybe? No? Great, so if we don't have more questions, maybe if you want to talk later. So thank you very much for coming. Thank you all the teachers and educators for
for coming, and the rectors for releasing you, and the students also for releasing you for coming to listen to Jim, who is like you had like so much experience, and we wanted to have somebody from NASA. I was talking to the teachers. We really wanted somebody from NASA to come and interact since so many years, and it's really a privilege for us to welcome you and to share
Well,
whatever experience you have.
every experience I've had on Mauritius has been warm, and I appreciate the welcome that I've gotten. I would like to take a picture back to my wife. Could we get anybody who wants to take a picture with me up on the stage and we'll take one big group picture?
Okay, yes. So thank you very much. We'll take the group photo and then we can go back to school.
Yeah, back to school.
I don't know how to turn that off.
They will, I think they will switch it off from upstairs.
Oh, I just turned it. Maybe we should turn the screen off. Oh, yeah, that's good.